So, welcome back. So, my name is Anil Yadav, and I am here for the tutorial 11 on fundamentals of semiconductor devices. So, today we will start with the optoelectronic devices. And actually, there are different types of optoelectronic devices. Optoelectronics means optoelectronic devices are the devices which uses the either the light energy to convert it into the electrical energy, or it uses the electrical energy to convert it into the light energy, like solar cells, photodetectors, or LEDs. So here we will talk about initially we will talk about the solar cells, and if you understand the concept of the solar cells, then photodetectors are the easiest to understand. And finally we will touch about the LEDs. So today most probably we will look into the basics of the solar cells, and from the basics to a bit of what are the different types of the solar cells, and what are the commercial, which are the commercial solar cells which are currently in the market, and what are the applications of the different types of solar cells, like tandem solar cells, silicon solar cells, amorphous silicon solar cells, and are uh, which are in the market and for what applications. Okay, so let us start with that. So I would like to appreciate this image. So here it is not for the solar cells, but it is an application of optoelectronic devices. So there are different types of photodetectors. Okay, so photodetectors which detects the light in the different ranges. So let us see in the wavelength regime. So this is the 100 nanometer, 200 nanometer, 280 nanometer. So this is the range, this is the spectrum of the wavelength. Okay, this is the spectrum of the light in the with the wavelength of the light. So from, let us say, 1 nanometer to say 1 micron around. Okay, so this is what we have, what is shown in this spectrum. It is the visible range of the light that we can see. Because of that we can see that this is a black pen, this there are different colors because of that only. Okay, so there are different types of telescopes and different types of photodetectors which are used in them to study the life in the external surrounding the in the like what to say, outside the world, outside our earth. Okay, so so how can we see uh, if we take the picture of the galaxies, how with the different cameras which detects the x-rays, UV light, visible light, infrared or radio waves. So these are the different picture of the galaxies or outside the world. So which are taken with the different type of the cameras. Okay, so with the x-rays, if you would be able to see the x-rays, so the galaxies would be like look like this entire world would be looking a different. Okay, if you your ability to see in the world with the UV light, if your eyes would be sensitive to the UV light only, not the visible range, so you would be looking at the at the galaxies. It would be, they would be looking like this. Okay, so these are the different applications. So of the photodetectors, this is just for the like in which are used in the telescopes only. So but in the IR cameras, so if there are IR cameras in the in market, you can buy one in the Amazon. Which uses the IR uh, detectors. So IR camera, what it does is, if there is dark, you cannot see in the night. So but if you fix the camera, you can see the moment of if there is someone outside your house or not. So these are gaining the advantages of because of the photo detectors. Okay, Now, first we will start with the solar cells. So why solar cells actually? So because if there are people say because of the environmental pollution, most of the energy is coming from the fossil fuels. Okay, so the industries, they are burning the fossil fuels or coal, these things, and from that we get the energy, and that we use for our household purposes. Okay, so but why not the wind energy, that hydro energy? Why not these things? Why only the solar cell? Because if you the energy requirement of the world is too much, that these, if we combine the whole hydel energy and wind energy, biogas energy, they cannot complete the requirement of the whole world. But the solar energy is the ultimate source of energy, which is solar sun is shining over our head, and we can get the we can convert the solar energy directly in the electricity using the solar cells. Okay, and one best advantage is, if you are living at the remote areas, you can, if you have the solar cell at your home, you are independent of everything. You do not require any kind of uh, lines, electricity lines. And because of that, it is gaining too much, gaining the momentum these days. And also, and there are other things. If you are sending some rocket uh, outside the space, outside our earth in the space, so you cannot give a wire and power that. You cannot have a fuel in that rocket, because it will be too heavy, and someday it will the fuel will be emptied. And on how that would work, that your satellite would work. So there are some high efficiency solar cells that are differently made for that, for the applications of the rockets. Okay, there are various type of solar cells. Like in silicon solar cells, there are crystalline solar cells and amorphous solar cells. Crystalline are a bit more efficient than the amorphous solar cells, as and they are a bit expensive also. And other, in terms of efficiency, there is not that much difference, but there is a difference. But these are cheaper, and in commercial applications that you would see in your houses, they are amorphous silicon solar cells only. And another one is the thin film solar cells. Thin film solar cells are like CIGS solar cells, and cadmium telluride, cadmium sulfide solar cells, organic solar cells, and perovskite solar cells, which are gaining the momentum these days. The research is too much oriented towards the perovskite solar cells, because of it is very cost effective, for the there are very cost effective methods to fabricate the solar cells, these kind of solar cells. And another thing is, cost per unit of the energy is important. That we will come on this cost per unit. If the solar cells are good, then whatever we are getting the electricity from the board, from the government, if it is cheaper or more expensive than the whatever solar cells are there. And world is becoming more solar every year, and that's why the prices are going down and down. There is much more research is going into these topics to reduce the cost of the solar cell and to make it more efficient. Okay, and okay, this lecture will be a bit different from the, it will be more conceptual rather than the mathematics into this. So there are some things which you should know, how these solar cells are gaining momentum, and how much is the efficiency of the current solar cells that which are in the market. So there are different type of solar cells that as I have already told you, there are multi-junction solar cells, single junction solar cells, and crystalline solar cells, thin film technologies, which are CIGS, concentrator. There is difference between concentration and concentrated and non-concentrated. Concentrated solar cells, as you might have seen some lenses, there are lenses, okay, if or mirrors, concave mirror or the convex lenses. In the convex lenses, what we can do, we can concentrate the light. If we have a bigger lens, we can concentrate whatever light over it to the to its focal point. Okay, so if we put a solar cell at the concentrated part, so it will be more efficient. It can generate more power because of the more intensity of the light at a very smaller area. Okay, so whatever we energy we are receiving, which is 1 kilowatt per meter square over the earth, whatever, this is the energy that we are receiving from the sun. But instead of making a 1 meter square solar cell, we can make it very small, and we can make a large concave mirror or convex lenses, so which can concentrate the light to a single point. This is the concentrator. Okay, this is the concentrator. And there are emerging PVs are dye sensitized solar cells, perovskite solar cells, perovskite, and another one is the tandem solar cells. Okay, the tandem solar cells and these multi-junction solar cells are kind of the same. Okay, so and these so this is the graph how the efficiency of the different type of the solar cells is increasing. Okay, so recently this is the graph of the of this perovskite solar cells, perovskite, which came in into the research in 2009. From that point it has gaining the graph is much more steeper than any other graphs of the solar graph of the solar cells. This is the efficiency, and this is the year. Okay, with the years how the efficiency is increasing. Okay, now currently the most efficient solar cell is the multi-junction solar cell. This is the multi-junction solar cell, 4 junction solar cell or more, to make the which is around 47.1%. And currently in this year, this is the data of 2022 2020, and currently it is around 49%. Okay, a 49%. These type of solar cells, are more are used in the satellite applications, which we want more efficient and have very less weight. Okay, so so the weight to efficiency ratio should be lesser. Okay, or we can say efficiency should be higher and weight should be as least as possible, so that it should so that we in the satellite should not be that much bulky. Okay, and another thing, this is the this perovskite solar cell, which is gaining the momentum now, and currently so many people are working on these type of solar cells, because there are various problems which people are encountering, and that's why these are not in the market. So people are working to make it more efficient as well as to make it more stable, as perovskites are not that much stable in the outer environment. So people are working on that. And same thing is for the organic solar cells as well. This is the organic solar cell which is gaining the momentum, and these are the things. So okay, and so for okay, what is a solar cell? Solar cell is which converts the light energy into the electricity. Okay, so how does it converts the light energy to the electricity? It absorbs the solar light. Okay, so this is the solar spectrum. This is the intensity, or we can say the spectral irradiance of the solar which is coming. Okay, this is the black body. What black body radiation, as we can say, sun is kind of a black body radiation, and every there are there are almost all whole wavelength spectrum is coming of is emitted from the black body, and that depends on the temperature. And this the temperature, because as it depends on the temperature, so this as we Wien's displacement law, I doesn't remember that thing. So Wien's displacement law is kind of there, so which shows that how the black body radiation depends with the wavelength. Okay, so this is kind of that. So and this is around the temperature of the sun is around 5250 degrees Celsius. This is the black body radiation. And okay, so which this is the wavelength of spectra which is emitted by the sun. Okay, so and this yellow color spectrum, so that you can see it is the spectrum which is outside the atmosphere of the earth. Okay, but as soon as it reaches to the earth, so this the some intensity of the light is absorbed by the outer atmosphere of the earth. Okay, there are some gases: oxygen, H2O, water vapors, N2, nitrogen, and there are several gases: carbon dioxide, carbon monoxide also. There are several gases in the atmosphere, which and ozone, which is this part as we can see. So ozone, which protects us from the UV radiation, and this part is absorbed. This UV region part is absorbed by ozone. Okay, and there are some these dips, which is because of the H2O and oxygen, as it has shown, and these are the bends. Okay, so the visible region is from 400 to 800 nanometers. Okay, the visible region is, or we can say about 750 nanometers. Okay, so this is the visible range that we can see, our eyes are susceptible to. Okay, so uh, and this is the peak of the solar spectrum, which lies around 500 nanometer. Okay, so and another thing, so okay, so how does a solar cell works is okay, that we will come in the next slide also. So okay, due to the atmosphere, 80% of the only 20% of the energy is absorbed by the atmosphere, and only 80% reaches to the to the earth's surface. Okay, so now huh, so okay, this is a semiconductor material. Okay, this is a semiconductor material. This is the length of the semiconductor material, and sun is shining from this side. Okay, so this is the conduction band, and this is the valency band, and absorb energy high. So solar energy, as it contains all the radiations of the from the a range of wavelengths are there. So this is blue light, which is very high energy, and this is the green, which lies in the middle, and this is the red, which has the low energy. Okay, so this is a semiconductor material which absorbs the light, and by absorbing the light, what it does is the electron from the conduction band jumps to the from the valency band jumps to the conduction band. Okay, so these electrons are there in the conduction band, but as you can see, the conduction band is flat. Okay, as conduction band is flat, but so if we take one connection here and one connection here, and put a resistive load there, so there won't be a flow of current, because there is no field in the semiconductor. There should be some field should be there, so that these electrons can move on a to the rest to one electrode, and if there are holes, as we shine the light. Okay, just a minute, someone wants to join. Okay, Okay, so now, if when we shine the light on a semiconductor, so electron hole pairs are generated. Always there is a transition of electron from the valency band to the conduction band. So always the generation of electrons and holes will be in a pair. So we always call it electron hole pair. Okay, EH. Okay, so there electrons are in the conduction band which move, and holes are in the valency band. Okay, so we need to separate these are in bound state. This is a electron and this is a hole, so these are in the bound state, so they will recombine, so there won't be any current. Okay, so how we can separate? There are several methods through which we can separate the electrons and holes, electron hole pairs. Okay, that we will look into how we can separate. Okay, so now huh, now if we apply an external force. Okay, if we apply an external force, we apply a voltage here. Okay, so what will happen is this is the electric field in this direction. So because of the conduction band and the valency band, now there is a gradient. Okay, now there is a gradient, because of that there is a field. So electrons will move in downhill, holes will move to this side, and there will be a current. But you can see that we are applying a field here. But what is the purpose of solar cell then? If we are applying a field, what is the purpose of solar cell? So this is kind of a photo detector. If we are shining the light, electron hole pairs are generated, and we have applied a field, and electron it will give a current. Okay, so initially when we haven't shined the light, there were a less number of electrons, the current was less at the time. As soon as we applied, we shine the light, there will be more number of electrons and more number of holes. So the in this case the current will be more. So it will give the indication that current is more now, and now we have shined the light, so it will so there is a light outside, so our detector will say that thing. Okay, so this is external force, but this cannot work as a solar cell, as we need power, but we are giving it power. Okay, but we are in need power. Okay, so this is the external force that we have applied. These electrons are moving this side, so this is electron current, we can say, but the current J will be in this direction. Okay, this is the depth of the semiconductor that we have taken, this kind of semiconductor. Okay, and now so how can we induce the electric field? So if as you must have seen that the last in the previous lectures that we have studied about some of the junctions. There were heterojunctions also, there were homojunctions also. In the PN junction, which is a homojunction. Okay, homojunction is because it both are the same semiconductor. Okay, which is a P type and N type. The basic material is the same. Homojunction is because there is no change in the band gap. Heterojunction may in heterojunction, what happens, there is a change in the band gap. That's why there is a sharp change at the bend edge, at the edge of the at the metallurgical junction. Okay, so in homojunction, so this okay, if we draw a Venn diagram of this one in this side, so this is a P type semiconductor. Okay, so this is a P type, this is N type, and light is falling in this region from the left. Okay, so the electron hole pairs are generated in the whole region. Okay, but most of the light is absorbed in this region. There is very less light which is reaching towards this region. But what we want, okay, if the electron hole pair is generated in the depletion region, this is the depletion region. If the electron hole pair is generated in this region, what will happen is, because of the electric field in this region, this is there is electric field which is built-in electric field because of the because of the there is a gradient in the conduction band and the valence band, which is due to the Fermi level should be Fermi level should be constant. Fermi level should be constant throughout the PN junction, throughout the PN semiconductor, PN junction semiconductor, PN because of at the at what to say okay at um, at what to say okay that is no need for that, but because of the Fermi level should be constant. Okay. Hmm. Okay, what to say that I forgot the name. I forgot that name. Don't worry. I will tell you about when I'll remember that. Okay. So, there is a PN junction. Because of that, there is a built-in electric field at this junction, and electrons will move in this direction, and holes will move in this direction. Okay. So, let me. Okay. Huh. Electron hole pairs are generated in this region. So electrons will move in this direction and holes will move in this direction. So they are separated because of the built-in electric field. Okay, because of the internal electric field, that is because of the junction. Okay, they are separated and they are collected at the respective electrodes. And if we connect this to a load, they will give a current. Okay, if because electrons will go this direction, hole will go this direction, they will give us a current. This is what we wanted. Okay, so there are several things that you need to note, that if the most of the hole pairs are generated in this region, which is the P region, this region, they won't be collected because they will recombine here only. But we do not want the recombination. Okay, we do not want the recombination. We want electrons and holes to be collected at the respective electrodes to give the current. So if they will recombine, there won't be any current. So this region should be as small as possible. Okay, we need this region thinner. Okay, we need this region thinner, so that most of the light should be absorbed in this region. Okay, and our depletion region should be as wide as possible. So we want this depletion region from here to here. This should be this W. Okay, this W should be more so that most of the light should be absorbed in this region. Okay, so how can we make this kind of junction? If we make P plus N junction that we have seen, so this is a kind of one-sided junction. Okay, and this is kind of one-sided junction in which the depletion region is more towards the N region. Okay, or we can make the N plus P junction. If we are taking it as a N side this side and P side this side, so if the light is coming from the N side, we can make it N plus P junction. Okay, so that the depletion region would be more towards the P side. Okay, so this is the kind of and there are several problems that we will see in next slides. So what are the problems and what are the solutions, and what are the problems that we are currently facing, and how the silicon solar cells are in the market, why they are why only silicon solar cells in the market. Okay, that we will see. So and so okay, so the electrons are going in this direction, so current J will be in this direction. Okay, J will be in this direction, so there will be a current, and holes are going in this direction, and J holes will also be in this direction. Okay, so the total current will be J because J electrons plus J holes. Okay, so that will be the total current. And okay, in the next slide that we so Okay, so this was a PN junction. Okay, this is a we will talk about currently we will talk about the silicon solar cell, PN junction silicon solar cell only. So this graph that you can see, okay, it will be a bit lower from, and this graph that you can see, which is dark, this is a PN junction this is the characteristics of the PN junction. Okay, when we shine the light, what will happen is there will be a current uh, in the opposite direction. Okay, if we apply the voltage in this direction, then we get the current. But if we are not applying any current, then still we are applying any voltage, then still we are getting the current, which is this thing. Okay, we are not applying the voltage, this is the v that is applied, and this is the v. What I have shown, this is the forward bias and this is the reverse bias, that we are not going to talk about. So this is the v which is generated across the solar cell. This is the v which is generated across the solar cell, from the P and the N that you will measure. If that also depends on the load, this load this load that you are connecting. If the load is, so this power, this is the maximum power point, and the load line moves according to the load. Okay, the load line moves according to the load, that's why there will be a different voltage for the different load. Okay, so the voltage can be here also, can be here also. This Vm that we say, Vm, which is the voltage at a particular load. Okay, so this is the current voltage characteristics. Okay, let us just come on the on solar cell characteristics, solar cell current voltage characteristic, which is this one. Okay, so this point, which is the at zero voltage, this point, the current at the zero voltage is the short circuit current, which is because of the when you just short circuit this. Okay, because there is zero voltage at this point, because we are just shorting the cathode and anode, so there will be a zero voltage, but the current will be very high, the highest current will be there, so which is the short circuit current. Okay, and when you open this, there is no load, when you measure the voltage across these 2 points, across the cathode and anode, so that will be the maximum voltage, which is the VOC, open circuit voltage. And at this condition, the load which is maximum, okay, load is maximum, R, which is maximum because it is infinite. We have opened the circuit, so so resistance is, load is infinite. Okay, so at that point you will get the open circuit voltage. And and another thing is the fill factor. Fill factor is the maximum power that you can get out of the solar cell. Okay, maximum power, P max, that you can get out of the solar cell, this divided by VOC and VJSC. Okay, this is the fill factor, and this gives the extent how much your this it is making a rectangle or square. Okay, how much this is making, this is the wasted energy, this is the way this comes because of the series resistance and all these things. Okay, we need this point VOC to overlap with this point. We can say this is the I max or J max, and this, no, V max, actually V max, and this is the J max. V max into J max is equal to the P max. P max is equal to I max into J max, V max. Okay, I max into V max. Okay, this is the power, that maximum power that we can get from a solar cell. Okay, we want these 2 points to overlap. Okay, so how can we do that? There are several things to decrease the series resistance, and that we will look into how we can reduce the series resistance so that this point can come closer to this. Okay, so this is efficiency is VOC into GSC divided by what the into fill factor divided by the power of light that we are the power of light which we are shining over the solar cell. Okay, now okay, there are several issues that in the solar cell that you should know about how we can improve the efficiency. We need eta to be maximum. Okay, how we can improve the efficiency? We can to improve the VOC and JSC. Okay, we will look into how we can increase the VOC and JSC and fill factor. These three things, how we can increase so that we can improve the efficiency of the solar cell. Okay, so JSC issue. So photon energy versus band gap. So if we, as we can see, so if we increase the photon energy, the band gap will be increased. Okay, so there was a solar spectrum. Okay, so in this direction we are decreasing the the band gap. EG is decreased in this direction as the wavelength is increasing. Okay, so if we increase the band gap in this direction, so if we increase the band gap, because to absorb the light, so this is the EG, this is the EG. So the wavelength of the light should be lower than the band gap energy. Okay, so or we can say energy of the light should be more than the band gap of the semiconductor. Okay, so band gap of the semiconductor, whatever the light, okay, let us say, so this is the at this point there so this is the our we have a semiconductor which has a band gap which is corresponding to 1000 nanometer of the wavelength. Okay, so whatever the light which we are shining over that semiconductor, so which is have higher energy than the band gap, or we can say lesser this wavelength than 1000 nanometer will be absorbed. So this part of the solar spectrum, okay, just a minute, I will change the color of the pen. So this part of the solar spectrum will be absorbed. Okay, which is less than the 1000 nanometer, but this part will be wasted. Okay, this won't be absorbed, and which will reduce the efficiency of the solar cell, because this is the total energy that we are getting from the sun. But this energy which is greater than the 1000 nanometer of the wavelength is wasted. Okay, that will pass through the solar cell, or will be absorbed by the other elements of the solar cell which cannot generate the electricity. Okay, so and if we increase the band gap, then if we come to the 750 nanometer of the wavelength, so this much. Okay, so if we come to the 750 nanometer, okay, if we come to the 750 nanometer, this part of the, so this much part of the spectrum will be absorbed, and this will be wasted. This part will be wasted. Okay, this part will be wasted, which will decrease the efficiency of the solar cell. Okay, which we do not want. So what we were saying in this one is, if we increase the photon energy, that is, if we increase the band gap of the of the material, whatever the material that depends on us. Okay, which material we are taking. Okay, if we increase the band gap, so this light will be absorbed less. Okay, one photon gives us one electron and one hole, okay, which gives us the photocurrent. But if the photons are absorbed less in the semiconductor, so there won't be so there will be less current. Okay, if photon energy, okay, if we are increasing the band gap is higher, or this photon energy is lesser, so there won't be any generation of the carriers. Okay, so therefore the current will be less. Okay, so we cannot go so why we want to increase the band gap of the semiconductor, that we will come why we want to increase the band gap. So to this is to increase the VOC. Okay, this we want to increase the VOC. There are two terms, VOC, JOC, no, JSC. Okay, if we want to increase the VOC, we need to increase the band gap of the semiconductor. Okay, so there is a trade-off in between these two. How if we increase, if how for how much we can increase the band gap. Okay, so now huh, okay, this was okay, it's here only. So photon energy, if we increase the photon energy, that is we are increasing the band gap. So this much part of the solar spectrum only we can absorb. Okay, this is AM 1.5. AM 1.5 is if this is the surface of the earth. Okay, this is the surface of earth, and if at the noon, so sun shines at our head. Okay, so this is the atmosphere which is surrounding the earth. Okay, it is suppose it is taking a length L1 L1 to cover, to reach the surface from this point, from the top of the atmosphere to reach to the earth. The distance covered through the atmosphere is L1, the from for the light. Okay, if the sun is shining at this point, which is after noon, in 4 o'clock, 3 o'clock, 4 o'clock, so it will be a bit aside. So the length covered by the light through the atmosphere will be a bit longer. Okay, so light will get absorbed in the atmosphere more. Okay, so this is AM1. If it is shining at our head, this is AM1. And if this is L2 divided by L1 is 1.5. So this is the meaning of AM. Okay, air mass, we can say air mass illumination, or air mass illumination only. Okay, so if this L2 by L1 is 1.5, this is AM 1.5. Okay, there is one term AM0. AM0 is outside the atmosphere at this point. Okay, outside the atmosphere is AM0, which can be used for the satellites, okay, which are outside the atmosphere. Now this is the solar spectrum which is reaching to the earth. Okay, so if it is already very less than AM0 or AM1. Okay, so and from this one, from this also there are these peaks which are absorbed because of the different gases in the atmosphere. And if we are reducing the absorption of light, then the efficiency will also be reduced. Okay, but this we do not want. Okay, so if the band gap is increased, then JSC is decreased. So this is the graph. Okay, this is the graph. This is the AM0 which I was telling you about, so which is outside the atmosphere. Okay, so you can see these dips are because of these dips. Okay, the dips in the solar spectrum, and which are these are in the range of the IR. Okay, these are in the range of IR, which is the lower band gap side. Okay, these are in the lower band gap side. Okay, these are at the lower band gap side, and you cannot see with here. Okay, that much dip. Okay, let us see, someone wants to join. Okay, now, huh. Okay, so now, if we increase the band gap, as in this side, this is the if we increase the band gap, then the JSC that we were talking about, JSC will decrease because we are absorbing less light. Okay, because we are absorbing less light, that's why the circuit current is decreasing. This is short circuit current density, which is amps per meter square. Okay, so now, so what is the solution? Okay, this cannot be avoided in the materials with the band gap, because if we are using silicon solar cells, if we are using silicon only, that we have already made our mind that we are going to use only silicon, then we cannot help. Okay, so another thing is, okay, silicon sol, the only thing is we can do different, we can get a stack of different materials. Okay, with different band gaps, easy. Okay, with different materials. Okay, so let us show you, which we can call it as tandem solar cells. Okay, in tandem solar cells, what is we can absorb the whole spectra of the light in different regions, or with different materials. Okay, so that I was saying about the multi-junction solar cells, it is the same thing. So if there are different materials, okay, this is M1, M2, and M3. Okay, light is coming from this direction. Okay, light is coming from this direction. Why there, light is coming from this direction. Okay, so the more okay, most energetic light will be absorbed in this region, in M1. So we want we so the whatever the wavelength of light which is lesser than the band gap of the semiconductor. Okay, this is the band gap of M1. If the energy of the light is less than the Eg1, okay, if the energy of light is less than Eg1, that will pass through it and will be absorbed by M2 and M3. Okay, so the stack should be such that M3 should be least, with the least band gap, then M2, and then M1 should be the with the highest band gap. The most energetic light should be absorbed by this one. If we do the opposite, what will happen is, so the most of the light will be absorbed by M3. The whole light will be absorbed by M3. So whatever it is, whatever, okay, M3 has the lowest band gap. Okay, M3 has the lowest band gap. So whatever light which has the energy which is greater than Eg3, okay, which is we are assuming. Okay, so in this spectrum, so the light which we were supposed to absorb by M1 will be absorbed by M3 only. So 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 we will get, current will be more, but this JSC will be more, which we were supposed to get in the with the M3 only. But VOC, that VOC will be very less, which will be corresponding to the band gap of the M3 material only. So there is no meaning of putting M1 and M2 in this case. Okay, so we can discuss more about this concept, more about this concept a bit later, when you will understand about the VSC concept, VOC concept. Okay, so there is another issue, JSC. JSC has another issue. If the material that we are taking is not sufficient to absorb the whole light. Okay, there is light, so So this is the silicon wafer. This is the thickness of the silicon wafer, which is we say 500 micron. Okay, this is the 500 micrometer, or typical silicon wafer. Okay, it is given at 180 micrometer, because in the solar cells the thinner wafers are used. Okay, so whatever we use for other purposes or for research purpose, we can use around 500 to 525 micrometer. Okay, so this is this depth, which is 180 micrometer. So whole light should be absorbed by this 180 micrometer thick silicon wafer. Okay, if it is not absorbed, then that is the, if it is passing through, then it is the wasted one. Okay, so this is the absorption coefficient. Okay, this is the absorption coefficient, or we can say absorption of the light, how much light is getting absorbed in a wafer. This is the wavelength of the light, and this is the thickness or absorption length, or this is the thickness of the wafer. Okay, this is the thickness of the wafer in this much thick wafer. This is the light absorbed. So this is the typical, this is the 180 nanometer. Okay, so above 1000 nanometer of the wavelength, the light is not absorbed by this 180 micrometer thick wafer. Okay, so this wafer cannot absorb above 1000 nanometer. So if the wafer thickness, if we increase the wafer thickness, then we can increase, we can go in this area also. Okay, so this is the wasted one. This is the, or where does it lie in the solar spectrum? It lies this much part of the light is wasted. Okay, so which reduces the efficiency of the solar cell. Okay, so there are some things which we can do with this one. We can without increasing the thickness of the wafer, we can do some coatings, so that we can absorb the more light. Okay, so how does it can be done is, so if this is the silicon wafer, this blue color. Okay, this blue color is the silicon wafer, which is say 180 micrometer thick, and if we coat a material with appropriate optical constants. Okay, with appropriate optical constant, which is say reflect with appropriate refractive index. Okay, so what will happen is, so if the light is coming, so if it is reflected back, so reflected back from the bottom surface of the silicon wafer, so it will continuously back and forth, reflect back and forth. So effectively what we have increased is, we have increased the length, effective optical length of the light. Okay, this light has to travel more and more, so it will be ultimately absorbed by the silicon wafer. Okay, so so this is the coating of the of a material with appropriate refractive index. Okay, and another thing should be done is, the bottom surface should also be done with some there should be a roughness. Okay, roughness in the sense, there should be, if a light is coming like this, so if the surface is rough like this, if light is coming like this, so it will get reflected back in this direction, in this direction it will get reflected back in this direction, like this. So like this we can increase the effective optical path of the light. Okay, if we can increase, so ultimately it will be absorbed inside the semiconductor, and which will increase the efficiency of the light. Okay, so so it will increase the current, and ultimately how current will be increased, because it will increase the number of electron hole pairs generated because of the absorption. Okay, so this was the initial JSC. This is the short circuit current density, JSC, with the thickness of the of the solar cell. Okay, cell thickness. Okay, initial without any coating. So after the light trapping, uh, no. I'm sorry. Actually, this is the lesser, na. This is lesser. So this is the initially which was without coating of this surface. Okay, and this is after coating, which is increased. Can you see? This is increased. The JC is increased. Okay, so and the more increment is in this region because we have increased the if our cell thickness is say 5 micrometer, which is in this region. So and 10 micrometer is there are two cells. Okay, so we are increasing the effective length in this region as well, and in this region is it was already more already absorbing more light because of the more thickness. Okay, so the effective so the current the maximum current could go this much only. Okay, the maximum current could go this much only. So the difference in the current will be more in the lower side of the cell thickness because we are the path L delta L or optical path delta LOP. Okay, I am just giving a name. Optical path of the light delta LOP we are increasing in this region more. That's why the difference in this region is more. Okay, and there is another issue. As if you have seen the silicon wafer, these are very shiny. Okay, you can see your face. They are like mirror. Okay, so most of the light which falls on the silicon wafer, it gets reflected back. But we do not want this light to be reflected. We want this light to be absorbed by the silicon wafer to generate electron hole pairs. Okay, if two electron hole pairs, so they they will be absorbed if we can do some engineering on the wafer so that the light should not be reflected back to the environment. Okay, so the light is reflected most in this region. Okay, in the UV region, and 30% around in between 30 to 40% is reflected back from the 500 to 1000 nanometer, and this 30% is too much. Okay, this 30% is too much. We do not want any light to be reflected back. We want all the photons to be absorbed. Okay, 60 to 30%, this is too much. Okay, wait. So this is too much. Okay, so we are directly losing the efficiency of the solar cell just by reflecting back the light which was coming on the solar cell. Okay. So how can we do that? There are several things. There are is one thing is the anti-reflection coating. If we can do anti-reflection coating over the surface of the this is the silicon. If we can do the anti-reflection coating or which is with a material with appropriate refractive index, so it won't let the light to be reflected back in the outer world. Okay, so and then anti-reflective coating, you can just search in the Google what type of anti-reflective coatings are done. Okay, so there are several materials. So actually I also don't remember that, and which materials they do. So they might be coming in the next slides. I have added some slides on that. So because of that, we can reduce the reflection of the light, and we can increase the absorption in this region, and ultimately we can increase the absorption of the light in this material, silicon material. And that optimum refractive index, there is the formula of the optimum refractive index, how much should be the refractive index n not n not n1. N1 is the refractive index of the material that should be coated over that, and this should that d1 should be the thickness of the material. Okay, so which is equal to square root of the refractive index of the air into the material. Okay, into the material on which we are coating, and accordingly we can adjust the thickness of the material over that. Okay, so that depends on the wavelength of the light, that is the most which is reflecting back uh, in the environment. Okay, so that depends on that also, and the this thickness of of the coating is depends on the refractive index of the same material which we are coating. Okay, and this is the example. So initially this was the reflection of the light. This is the bare silicon which is was reflecting. This is the wavelength of the light in micrometer, which is zero point 0.4 micron to say it is given to 1.2 micron here. Okay, so this it was reflecting back around more than 30% of the light. Okay, more than 30% of the light was reflected back in the environment. So or and another thing is, over the silicon solar cell there is a toughened glass over that. Okay, to protect it from the outer environment, or there is kind of a hailstorm or so it this glass protects the solar cell. Okay, because silicon is a brittle, so whatever you do, if you throw a small stone over that, it will get broken. Okay, so to protect that, there is a very thick glass over that, which is about 3 to 4 mm. So after that, this also reduces the reflection of the light in the outer environment towards the outer environment, and also improves the efficiency. And after the coating, after anti-reflection coating with n is equal to 2.3, it is given. So we and of 60 nanometer, it is calculated from this formula. Okay, it is calculated from these two formulas, and this optical, as you can see, this anti-reflective coating is done for a particular wavelength. Okay, that particular wavelength is around this point, which is 0. 0.6 micrometer. Okay, so whatever this lambda naught is nothing but 0. 0.6 micrometer. Okay, so at this point only you can see that reflection is 0%. Okay, this is because of that only. This is because of that only. It is this anti-reflection coating is done corresponding to 0. 0.6 micrometer wavelength. Okay. So by these several methods, we can increase the JSC, which is the short circuit current, which helps to improve the efficiency of the solar cell. Okay, and now another solution. This is to increase the light trapping. Okay, that I was telling you about the roughening or surface texturing. This is the bottom surface, and light is coming from this direction. If it would be flat, what would happen is, this is flat, so most of the some of the light is getting reflected back, that we have seen here. So some of the light is reflected back. Okay, and to avoid that, what we can do is, one, we can do the surface texturing also, and over that we can do this anti-reflective coating, ARC. Okay, anti-reflective coating. Okay, so and if the bottom surface is also rough, so light won't get passed through that much easily. Okay, if light is passing through this, so then on also we are losing some of the efficiency that we have seen at this point. Okay, if it this point, if this is very smooth, so we can lose. And this and also this we will lose this part of the spectra if we are decreasing the thickness of the wafer. Okay, if let's say we are just taking the 10 micrometer of thick wafer, so we will lose this whole part. If our if film thickness, okay, if the film thickness is very less than the very less, so we will be losing this. So but we can increase the efficiency even in a thinner wafer by these several engineering. Okay, okay, several processes that we can do by increasing the roughness of the bottom, and doing the roughness surface engineering texturing at the top and bottom, and plus increasing this plus depositing this anti-reflective coatings. Okay, so through this we can increase the light trapping, so which will increase the short circuit current. And this is the same image of the FEACM image of the okay, sorry, of the textured surface of the silicon. Okay, so which is like this only. Okay, so whatever the light, if light falling at this point, so it will get reflected, and from the at the top also there will be there so at the top also there will be some anti-reflective coating. So there is anti-reflective coating which will reflect it back. Okay, which will reflect it back, and so okay. And there are other things other than this surface texturing is done to, if the light is coming in this direction, okay, let us say in this direction, it will get reflected in this direction. Okay, it will get reflected in this direction, some of the light will get absorbed through this. Okay, which is, we can say, transmitted in this, and will get absorbed in the deep down of the silicon wafer. Okay, so too many reflections and it will get more absorbed more. Okay, it is shown in this one. So reflected, some is reflected back, and this is refracted, this is refractive. So more we can, through this we can collect, we can get more and more light absorbed, and which will increase the JSC. Okay. Now let us come on the another issue, which is a big problem. Okay, which is the VOC. This is the issue one, which is VOC. So VOC, as there is a formula that you must already have read in the lectures also. So I can okay, I am not going into the mathematics, I will just tell you about that thing. So VOC has direct relation with the band gap. If we increase the band gap, VOC will increase. Okay, just remember that thing. If we increase the band gap, this VOC that we were getting in this one, in this graph. Okay, this is the VOC, this is the VOC, short circuit, no, open circuit voltage. This depends on the band gap of the semiconductor that we are using. Okay, so so if lower the VOC, lesser will be the no, lesser will be lower the band gap, lesser will be the VOC. Okay, so there are if we want to increase the band gap, if we are increasing the band gap, then we are losing the JSC, because if we are increasing the band gap, we will absorb less light from the solar spectrum. Okay, in this case, if we are increasing the if we are increasing the band gap, which is in this direction, if we are increasing the band gap, we are absorbing only this much of the light. Okay, then we are losing the JSC. Okay, so that also we do not want to do. So there is an optimum uh, relation that we need to use an optimum kind of a, a semiconductor, so from where we can get the maximum efficiency. Okay, So the product of VOC and JSC should be maximum kind of. Okay, so then only we can get the maximum efficiency. Okay, so so this is the band gap. Okay, this is the conduction band, this is the valency band. So when we shine the light, electrons are transferred from the conduction valency band to the conduction band, and electron hole pairs are generated. So this happens this happens when the wavelength of the light or the energy of the light is exactly equal to the band gap of the semiconductor. What say if the energy of the light is more than the band gap of the semiconductor, so the electron is transmitted much higher energy level at the in the conduction band. And so this energy there is nothing in this energy. So if this is the energy which is wasted as a heat in the in the semiconductor itself. Okay, this energy is wasted. Okay, so this energy we cannot use, we cannot actually this is, we can call it a thermalization loss. Okay, which is given here. This is the thermalization loss if the band gap, if the photon energy is very higher than the band gap energy. So what here comes the thing, that tandem solar cell, but that I won't tell you now also, because we are discussing the issues. Okay, so I will tell that we have already seen also. Just I have just given a brief. If we can just put one more semiconductor here. Okay, one more semiconductor with a higher band gap, which is corresponding to this, that will absorb this light. Okay, will give you a VOC which is corresponding to that band gap. Okay, which is corresponding to that band gap, and the thermalization loss will be lesser in this case. Okay, so there are some things which is but to fabricate those type of solar cells, it is a bit difficult. It is very difficult to deposit a layered semiconductors, too many layers in a semiconductor. Okay, so that will be difficult. So this is the issue. If we increase the band gap of the semiconductor, then we are losing the JSC. If we are decreasing the band gap of the semiconductor, we are losing the thermal the J VOC, and we are losing the energy as a thermalization loss. Okay, so what to do? Okay, so the issue is the band gap, that I have already told. The issue is the band gap. If we increase the band gap, we can increase the VOC. Okay, but at the same time we can lose the JSC. This is the thing. Okay, so and okay, so the issue of the VOC is solved in that with the band gap. Okay, there is another issue. There is another issue. We are losing the VOC. We are losing the VOC because of the okay, surface recombination. In ideal case, what happens is, this is N plus P junction. Okay, what I told you about, that there was a P plus N junction that was like this. Okay, uh, just think whatever be the junction there, that doesn't matter, there is a PN junction only. Okay, so if we are shining the light at this junction, okay, so electron hole pairs are generated in in the in the depletion region. Electrons are going this way, holes are going this way. Okay, but in reality it doesn't happen. If the electrons are generated at the edge of the depletion region, at the edge of the depletion region towards the P side, it at this edge, so what will happen, there is a very high probability of these electrons to going this direction, and these holes can be go this direction in this case also, and also the holes can go in this direction also. Okay, so if the electrons are going in this direction and they are collecting in this region, so they are so they are decreasing the efficiency of the solar cell, but we wanted these to go in this direction. Okay, so they we are losing our open circuit voltage at this point. Okay, we are losing our open circuit voltage at this point. So but we do not want to go these electrons and holes in the other directions other than this. Okay, so electrons go should go this direction and holes should go this direction. but but in reality this happens. Okay, at that point we lose some of the efficiency of our silicon solar cells. And how we can improve this thing, there is a okay, just a minute. Huh. Huh. So what we can do, if they are if the electrons are going in this direction, what if I can make a hill over this hill at this point. If I am making a hill at this point, what will happen is so they cannot climb, these electrons cannot climb the hill. Okay, they will be pushed back, they will reflect back at this point and will be collected in this region only. Okay, so this term if they are recombining at this point at with the they are going in this direction and recombining at this point with the anode. Okay, with the with the holes at the anode. So it is known as the surface recombination. We want this surface recombination as least as possible, so that's why we have made a hill. So this is p type silicon. If we can make this p plus junction at this point, if we can make it a bit more p plus, so there will be a hill. So this is the this is the Fermi level, this is the Fermi level. Okay, if we make a hill p plus junction at this point p plus junction, so it the Fermi level will be more closer to the valency band, so it will go like this. Okay, it will go like this, and there will be a kind of hill at this point like this. Okay, like this. Okay, so electrons will get reflected back, and it will reduce the surface recombination. So this is how we can improve the efficiency of the solar cell at of the silicon solar cell. Okay, so and another thing is this is p plus junction, this is okay, and this is known as the back surface field. This is the at the back surface. Okay, this is the front surface, light is coming in from this direction, and this is the back surface. And there is one more term, this is which we can do at the front surface also, to reduce these sir this recombination of these holes. To reduce this, we can make it a bit more n plus plus n plus plus. Okay, this region, at this region n plus, that is a front surface field, and this is back surface field. These are some of the engineerings that is being that has been done to make the solar cell more efficient. Okay, most efficient. So the graph, the initial graph from the NREL that I had shown you the in from the second on the first on the second or third slide, so that was because of these breakthroughs only. There were some there is a breakthrough in the efficiency of the solar cell, silicon of solar cell, which was around 15%, and it is jumped from 15 to 21%. That was because of these kind of the breakthroughs only. Okay. People understood these things, that there is a reverse current which is flowing because of the surface recombination. If the circuit initial the current should flow in this direction, electrons flows should flow in this direction. Okay, but because of the surface recombination, the current is flowing in this direction. Okay, electrons are flowing in this direction, which is reducing the efficiency. People understood that thing, because just imagine, just appreciate the thing, how much people have put the efforts to understand these things. Okay, there are some things uh, in instead of solar cells you should look some videos or some fabrication techniques which had put to fabricate the blue LEDs, which was the hardest task in the whole world uh, against the research community. But because of that blue LEDs, you are seeing the light around you. Okay, the the LED lights that in your homes, which they are the blue LEDs with the phosphor coating. Okay, so this was the very hardest task I think. So this was the big breakthrough. This was the breakthrough actually to fabricate the blue LEDs. Okay, and this okay, now let's get back on our topic, that which is the solar cell only. So okay, so huh, now VOC solution that we have already given, and point contact and back surface field. Okay, so there is one more thing, point contact. Okay, so what if this is the P plus silicon solar, this is the P silicon, this is the okay, this is the P silicon, light is coming from this direction which is absorbed in the whole region, and some of the electrons which were going in this direction. So there were two things which were done, which is done, one is to make this point a P plus, okay, to reflect back the electrons. And another thing is if we coat this, if we coat this with a high wide bandgap semiconductor. Okay, wide bandgap semiconductor, so that these electrons should not go through that. Okay, so this is the conduction band, this is the valency band of that semiconductor, which is the SiO2. Okay, this is the SiO2, silicon nitride, Al2O3, which can be coated, and electrons will get reflected back. Okay, electrons won't cannot be collected at this, or cannot recombine at this junction. There won't be any recombination. But what will be the problem is there will be the photocurrent, that how this photocurrent can be there. Okay, so these holes also cannot go. Okay, they will also get reflected back. Okay, but we do not want this to be happen, because we want these holes to be collected at this point. So what we can do is we can also coat the P plus and SiO2, but we can make a hole through that. Okay, we can make a hole through that, so that at a very single point we can collect the electrons. Okay, at a single point we can collect the electrons. So this will further reduce the recombination, the surface recombination. Okay, so which will further increase the VOC. This is the point contact that we can say. This is the point contact. In the next slide, okay, these are some of the issues. Okay, there is that thing. Okay, in this one I will show you. Huh. So these are the point contacts. Point contact plus surface field. Okay, point contact plus back surface field, both with the combination of both we can further improve the efficiency of the solar cell. Okay, so these things, whatever I am telling, or what I am teaching you, so these are the conceptual things. I have reduced the maths completely. I am not discussing the mathematics, but if you will ask about the mathematical part, I can show you that too. There that also that thing you can get from the notes, from the lectures, but this is a completely different thing. This is the reality of the silicon solar cells. Okay, this is nothing like that, just p n junction can make the solar cell, but there are several layers that you need to code, or that you need to do. So just appreciate that thing. This, there is a this layer, this layer. So how this, how this, the fabrication of the solar cell with the different layers, is it is increasing the cost. Okay, it is increasing the cost. So if you are saying, so that silicon solar cell is cheaper, okay, but not. But as these solar cells are not cheaper, that's why the in the market, if you are going to buy a silicon solar cell, they are not that cheap. Okay, but if they are going for the long term, obviously you are getting benefited for the long term, but they are not cheap, because the method of the deposition, this is being done, this n plus and p plus region, these are done with the diffusion. For these, to do these things, you need a very high quality clean room. There should not be any impurities in that. Okay, so to coat the SiO2, you need, big machineries. Okay, even to fabricate, to get a silicon wafer which is not fabricated. Silicon wafers are not made in India. We import silicon wafers. Okay, there are some solar cell companies which make solar cells. You can say that made in India solar cells, but they are not actually the made in India solar cell. The basic thing, which is the silicon wafer, we import. Okay, so recently there are three industries, semiconductor industries, that our prime minister has inaugurated recently too in Gujarat. One is in Assam. So they are aiming to make the silicon wafers in India. So then we can say, we can appreciate that thing, that a completely indigenous solar cell, okay, which are made in India. Okay, now there are, if you go to Tata Industries, Tata Electronics. Okay, so there are some solar cells, silicon solar cells, which come. There are several companies. One is Tata, that I visited once. So with they import big silicon wafers. Okay, so from that, and these silicon wafers, these are not cheap. They are there are several grades of the silicon wafers. One is electronic grade, one is solar cell grade, one is just research grade silicon wafers. So that silicon, the solar cell grade and electronic grade wafers, they are the most expensive. Okay, they are very expensive, and not they are that's why the solar cells are very expensive. We, whatever we have in our homes, or whatever you have seen over the roofs, they are not crystalline solar cells. The reason is, crystalline solar cells are very expensive. Okay, so and the efficiency, there is a bit difference in the efficiency. Whatever you get in our homes, it is around 20 to 21%. If you get with a crystalline solar cell, it is about 25-26% of the efficiency. Okay, so we can so to make it affordable, so amorphous silicon solar cells can work as well, because on our roofs we do not have the limitation of the space. Okay, so to get that same energy, we just need a bit of more area. Okay, so that's why. And okay, another thing is, okay, this is the fill factor issue. Fill factor issue is the resistance losses. Okay, in a solar cell, this is the solar cell. Okay, wait. This is the solar cell. That's it. So electron and holes has to travel through these known these areas which have no field. Okay, the field is zero, in this, because the it is flat. the conduction band and valence band flat. So this region electron has to flow in this region, this much region. So there will be a resistance because this is a p-type silicon, but p-type silicon is there, but there will still be, there will be some resistance in this region. Okay, to decrease the resistance you can increase the doping. Okay, to make it you can increase the doping, but again there will be other problems. So if you increase the doping, there will be this back scattered, or the, this hill will be lesser. Okay, and another effects will also come. So if you increase the doping of this region, so it will reduce the w, which is the depletion region width. Okay, so ultimately you are losing the efficiency again if you increase the doping. So the fill factor is because of the resistance losses in these regions, or the whatever you are connecting there is a metal contact here and here. Because of this is the series resistance. Okay, because of that series resistance you are increasing the you are decreasing the fill factor. Okay, the p type silicon layer and n type silicon layer. Okay, these are p type and n type silicon layers. Okay, this region and this region. Okay, because of that there is a resistance loss. Okay, how can you improve? Increasing the doping. But downside again the recombination loss, which is this recombination loss. Okay, and you are increasing, and another thing is this the depletion region width you are decreasing. Okay, that is again a loss. Another thing is the metal and semiconductor contact. Okay, so there is loss at the contact because of the Fermi level mismatch. Okay, so if you increase the doping, you can increase the doping also. Okay, so but at this point if you increase the doping, then it will increase the recombination loss. Because as we in recombination we have done that it is directly proportional to the doping, that n or p. Okay, you just check that there is a direct relation with the with the number of electrons or number of holes in the conduction and the valency band respectively. So it will increase the recombination. Okay, so and the metal, if we try to change the metal, so that will that the metal that, like if we are going for a platinum, so platinum is very expensive. If we are going for gold is expensive. Most of the metal in the silicon solar cells, it is silver is used. Okay, so if we are going for other higher no quality metals, so the cost will be higher of the silicon, cost of the solar cell will be higher. Okay, that again the same thing, metal layer, again the same thing, higher will be the cost. Okay, thicker metal layer, higher will be the cost. So if we increase the thickness, okay, one more thing, why thickness? Okay, so in a solar cell, so okay, why thickness, I'll tell you why thickness. So it is a bit important, so not that important, but you should know about these things, that's it. So okay, this is the solar cell, this is the top contact of the front top view of the solar cell. So the metal layer is how there is a strip of metal here, and there are like these. Okay, these are the strips of the metal. Okay, these are the strips of the metal which are, so the thickness, this strip, we cannot widen the strip, so because if we widen the strip, so this is the strip. Okay, this is the strip. If we widen that strip, this is the finger or this is the metal. Okay, if we widen the strip, what will happen is it will block the light. Okay, ultimately we will lose some of the efficiency because of the blocking of the light. the light is not absorbed by the material that we want, but it is reflected back by the metal contacts. Okay, that's why we cannot increase the width of the metal layer. Okay, but if no, okay, if we increase the width of the metal layer, that will decrease the series resistance. Okay, that will decrease the series resistance, because why? The metal contact is there, but we are taking the current out at the edge. Okay, from here, from if an electron is collected at this junction, it has to travel through the wall, but so there will be resistance through the metal. Okay, through the metal itself. Okay, so because the thickness of the metal is around 100 nanometers only. Okay, that 100 nanometer thick will be more resistive than 200 nanometer. Okay, 200 nanometer, or the thickness, which is so if we increase the thickness, then we have to 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 give more material will be required, more silver will be required. Okay, more silver will be required, that will ultimately increase the cost of the solar cell. Okay, so higher will be the cost. So this is the thing. And another thing is the power conversion efficiency, that we have already talked once about this thing. So which is the power conversion efficiency is JSC VOC into fill factor, which is directly proportional to and divided by the P. Okay, that P, P light, and also no, not in this case. P is okay. Just a minute. Hmm. 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 This is the P max. Okay, P max. VM IJM divided by VOC JSC. Okay, हाँ ठीक है ठीक है, हाँ हाँ, this is correct, this is correct, this is हाँ, this is JSC into VOC multiplied by fill factor. Okay, this is the efficiency. So there is a limit, so how much band gap we can increase, so that we can increase the VOC. If we increase the VOC, we can increase the VOC up to a certain range, increase the band gap up to a certain limit. Otherwise we will be losing the JSC. ठीक है, if we increasing the JSC, we are increasing the band gap, we are losing the JSC. Okay, this is the band gap. So this is kind of the we are losing the JSC. Okay, this is the JSC we are losing, and this is we are increasing the band gap, we are increasing the VOC. So this JSC multiply VOC, so there will be a trade-off. So this the graph of the multiplication, the JOC multiply JSC multiply by VOC will be a downward U. Okay, this kind of, so there will be a maxima of this JSC multiplied by VOC. Okay, this maxima is the maxima corresponding to the wavelength, whatever the wavelength it is. Okay, so that is the maximum efficiency we can get out of a solar cell. Okay, this is the maximum efficiency we can get out of a solar cell. So this is the silicon solar cell, which is around 1.1 electron volt, 1.1 electron volt, and this maxima we can get it around 1.3 or 1.4 electron volts. Okay, this is the maximum efficiency of the solar cell. Around this maximum efficient around this band gap, we can get a maximum efficient solar cell. Okay. Now just a quick recap. So one thing, there are okay, so initially we had a semiconductor, piece of semiconductor. Okay, this was the conduction band, this is the valency band, electron hole pairs were generated, this is electron, this is hole. Okay, this is electron, this is hole as soon as we shine the light. Okay, of uh, of energy greater than the wavelength, greater than the band gap of the semiconductor. Okay, but we need to we need to separate these electron hole pairs. These are in a bound state, but we need to separate these to the respective electrodes to get the current. Okay, so in silicon solar cell there is a built-in electric field at the PN junction that we have already studied. Okay, we do not give do not want to give an external energy. If we are applying the field, what is the point of having a solar cell? Okay, so there is a built-in electric field at the with the at the junction, PN junction. So because of that, electrons and holes are separated.
Hello.
Hello.
Hello. Excuse me, sir.
Yes.
Sir, I'm Indravarman, sir. I have
One minute.
uh,
Let me increase the volume. Yes.
uh, sir, do we have any sample papers for this NPTEL courses, sir? Semiconductor devices course.
Sample paper. Do you have all the assignments?
Yes, sir. Yes, sir.
Okay. The assignments are sufficient for that.
Sir, then how will be the questions asked, sir? Will it be objective type questions
Actually,
or writing it theories?
that will be decided by the course instructor. I am a TA of the course, so I cannot.
Okay, okay.
I am not making the paper. Okay, so
Okay, sir. Okay.
huh. So the even I didn't make the assignments. Assignments
Yes.
were made by a other person. So if you have any doubt in the assignments, you can discuss. You can drop a mail to me also. Okay.
Okay, sir. Okay, sir.
Yes.
Sir,
Huh.
what is your mail ID, sir? May I know?
Okay. Right. Okay.
Yes, sir.
Okay. I will write it in the chat box. I'll write it. Okay. Okay. Just a minute. Okay. Just a minute. Okay. Uh, you were not able to see the screen.
Sir, yes, sir, I consistently try to tell you, sir, but nothing worked at the time, sir.
Okay, actually, you should have turned on your mic because I could not see the. So you were not able to see the screen. Now you are. You can see or not?
Sir, now the screen is okay, sir. Now you are showing a quick recap, sir.
Yes.
But
Before.
while you're teaching, you have written something on the screen, but nothing was visible to me, sir. The screen was still the same
Okay.
as
Now
the
now
first
you
one.
can see that.
Sir, yes, sir. Now it's clear, sir. But
Okay. Now
uh,
red color.
sir, yes, and
Okay. I didn't know that. Okay. You should have turned off
okay.
on your mic. Actually, I could not see that thing. Okay. So okay. Write down my mail ID. Anil
Yes.
Yadav. anilyadav.iisc@gmail.com.
Anil Yadav dot
iisc
IISC.
at gmail.com. Okay.
Okay. Thank you.
Okay. Yeah. So okay. Now can you see the screen?
Yes, sir. Now it's clear.
Okay. 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 Actually, I didn't know that. Sorry for that because you should have turned on your mic and you should have told me. Uh-huh. Okay.
Okay, sir.
Okay.
I
No
I
problem.
will inform you next time. Sorry,
Okay.
sir.
No problem. So for the okay, there are there is a field, built-in electric field in the PN junction silicon solar cell. Because of that, we can separate the separate the electron hole pairs. Okay, separate the electron hole pairs that are generated because of the light. And there are three important parameters in a solar cell, which is a fill factor, and another is short circuit current and open circuit voltage. So these defines the efficiency of the solar cell. So yeah, this JSC increases with the trapping of the light, which is because of the absorption of the light. More the light is absorbed, more will be the JSC. Okay, more the intense will be the light, more the will be the JSC. And VOC is increases with the reduced surface recombination that we have seen in the back surface at the we have improved this VOC by back surface surface field. Okay, and by the coating of with the coating of silicon oxide, silicon dioxide or aluminum nitride and all these things. Okay, and one is the fill factor. Fill factor increases with the reduced internal resistances, which we can improve, which we can improve with the doping or some other things. So by reducing the size of the P and N part of the silicon solar cell. Okay, so now this is a kind of real life silicon solar cell, which there are several things that you can notice in this solar cell. Okay, this is a kind of a real solar cell, prototype of the real solar cell. Okay, this is pictorial representation, and in this one you can see there are this is the this is like to increase the trapping of the light. There is a surface texturing. Okay, to increase the light trapping, there is a surface texturing. So and another thing is which is done, this is the surface texturing. Okay, what is this layer that I want to know is hello.
Sir, sir,
Yes,
again the slide is still stuck in 164th slide, sir.
164th. Okay, so okay,
165th. Now it's okay.
which one it 160 okay, which you can see the this solar cell diagram right now.
Yeah, sir. Now it's visible, sir.
Okay, but I don't know why there is a problem. Okay, I will write here only. Okay,
Okay, sir.
this is the whole this part is the silicon. Okay, part is the silicon, which is, and this junction, this is a P silicon, this is P silicon, that kind of a yellow color, light yellow color, and this magenta color, which is kind of this is the N junk N type silicon, and this the junction between the magenta and light yellow, which is the PN junction. Okay, and this is the front surface speciation. Okay, this is the front surface field, which is highly doped, or we can say this is the or SiO2. This is the SiO2 only. This purple color type. Okay, this is SiO2. Okay, which reduces the recombination or surface recombination in the on the front side. Light is coming from this side and it reduces the recombination at this surface. The what we can say, it is mainly reducing this is N type now. N type is it is reducing holes to recombine at this surface. Okay, and this this part is N plus. Okay, this part at this junction, it is the N plus, which is the front surface field, FSF, we can say FSF. There was back surface field BSF, which is the this part this part is the back surface. This P plus region, a bit dark yellow, this is the P plus region, which is the back surface field to reduce the surface recombination. Okay, and this is the rear contact, which is the gold or ITO. Okay, and this is the front contact, which is just a finger, or we can say a strip of silver, which is AG. We these are get deposited. Okay, so so this is kind of a these many things are there in our solar cells which are commercially available. So there is a surface texturing to trap the more and more light. There is a very thin n plus region, thin n region, and there is n plus region to reduce the this front surface recombination. There is this p region, there is p plus region, there is SiO2 region in this one, and there is a back contact. So just see how many layers are there to make a solar cell, silicon solar cell. Okay, so these are not that easy. Okay, these are not that easy. So that's why the cost of fabrication is very high in this case. So there are other type of solar cells, okay, which are gaining the momentum or which are covering the market these days, which is a kind of research focus of the many researchers, which are the thin film solar cells. Okay, in thin film solar cells there is a there is a absorber layer which is very thin. Okay, which is in in of several microns, 1 or 2 micron thick. Okay, just this much thick layer can absorb the light and convert it to electricity. Okay, so that we will see how these are made. So why we are transferring towards these type of solar cells which are thin film solar cells from the bulk solar cells which are PN junction solar cells. Okay, PN junction solar cells are a bit, just appreciate the fact how much energy intensive to make a silicon solar cell is. Okay, initially we can just take a sand. From sand we are making a solar cell. So it is not an easy task to make a silicon wafer from the sand. So they are these quartz is the raw material for that. Okay, so there is metallurgical grade silicon which is so there is too much of metallurgy involved in this one. So silicon metallurgical grade, it is converted into the metallurgical silicon grade and polysilicon grade silicon. And so these are done at very high temperatures. Okay, the temperature is at around thousands of degrees of the temperature, and a very clean environment is required at this stage segregation. And at this stage very clean environment is required in crystallization. Okay, this very clean environment, let us say, is a clean room is required, which there are grades of the clean room. Okay, there are grades of the clean room, and to maintain these clean rooms it is very costly. So that's why India does not have that facility, because it is very expensive. Okay. So but India is making its own clean India is targeting to make its own chip and its own wafers in Gujarat. Now by 2026 we can get the silicon wafers from made in India only. Okay, so but this is a very highly energy intensive, and from that we make the solar cells. Okay, which is not an easy task this till this point. Okay, till this point this is not that easy task. Okay, from that we make the modules. So from here to here to go, so it is very expensive. So if you just think about, you have a glass substrate and you can just coat your material, just paint a material and you can get a solar cell. Just think of that thing. So these are kind of perovskite solar cell, organic solar cells are such kind of the solar cells. Okay, you just take a material and you just paint it like a brush and you can get a solar cell. But but there are other issues with these type of cells, like stability issue and open circuit voltage and JSC. These are the issues which are lower. Okay, so they are not that much efficient and not that much of stable that as this silicon solar cell is. Okay. Hmm. Now, so silicon solar cell wafer is around this much of thickness, which absorbs the light. Okay, so it takes this much of the thickness of the wafer to absorb the light. But what if there is a glass or metal foil? Just a glass which is not that much expensive. You can get it is very easily, and just paint a thin film of material. Okay, this is around 4 micron only, which can absorb the whole solar whole intensity of the light in this much thickness only. Okay, so so we are going towards that to make it more cost effective. Okay, so but these are let us say we are not going towards the organic now, but just think of a inorganic solar cells. So let us see, there are some solar cells which are like CIGS, and there are other solar cells also. So in these thin film solar cells, how does it work is there is a very thin film of the absorber layer we say, which absorbs the solar spectrum. Okay, this is the absorber layer, and this is the whole these there are three layers. These are the three layers which are main. Okay, one is hole blocking layer, one is absorber layer, and one is electron blocking layer. So it blocks the electron for the back surface, uh, to prevent the to prevent that recombination. Okay, surface recombination, which was the back surface field. This is the front surface field. This is the hole blocking layer. So these are the three main layers. Okay, so which is very thin, not that much thick, which is 180 micron or so. Okay, so and this is surface of the like cadmium telluride. So this one also takes many layers, which are this one is this SNO2 is nothing but I think this is tin oxide. This is electron transport layer or hole transport layer. Okay, that I don't remember. Huh. So this is one is the electron transport layer, one is the hole transport layer, and this is the back metal, and these are the things. So these are not that much thick. That can you see? This is the absorber layer is 2 to 8 micrometer only. Okay, these are very thin, not that much. So these are thinner. Okay, so these are grown, we do not require that long process, this is the long process to make a pure crystal silicon wafer. Okay, in this case silicon wafer is not required. We directly deposit these layers over the glass substrate, the glass that we have in our homes. Okay, directly we can deposit these much layers. But again, there is one more thing, one more problem comes in these. To deposit these layers directly takes these expensive instruments, which are thermal evaporation, thermal evaporated we can do, and e-beam evaporation, epitaxial growth, atomic layer deposition, chemical vapor deposition. These kind of the instruments are used, or there are these kind of laser pulse laser deposition. A laser beam goes on a material that evaporates or ablate the material, and which from that gets deposited over this substrate. Okay, so which are all these are also energy consuming, but there is not that much long process which is required in this. Okay, which is required. So we are saving the environment on one side, which we are saying that we are not burning the fossil fuels, but to get a silicon wafer we are using a lot of chemicals also. Okay, at these stage we are using a lot of chemicals which we are ultimately at one point we are polluting the environment. Okay, so so in these cases we are directly depositing these materials, and still there are some other factors also. Well, so now becomes there is one more type of there are other also organic solar cells, uh, dye sensitized solar cells, but I am just giving you a hint how these are deposited. These perovskite solar cells and organic solar cells have the same methodology to make these. Okay, same methodology is there are processes. You can there is a solution. Okay, you can make a solution of the material, say perovskite organic. Okay, organic solar cells are directly you I was telling you about that painting a material over a substrate. Okay, you can paint a material if you can make a solution. Okay, so these perovskite solar cells or organic solar cells, you can make the solution of the material, and you can just drop the material over the substrate, and you can just deposit that layer. Okay, that this layer, this is the TiO2 and CH3, this MAP, or methyl ammonium lead iodide. Okay, this is methyl ammonium lead iodide, which is a perovskite. So this material is the absorber layer, and the absorption coefficient is very high of this material. Absorption coefficient is very high, and only very thin, around 200 nanometer of the of 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 thin layer is required to absorb the material, not even in microns. Okay, so very thin is required, and above that the best part is the deposition technique. We do not require a sophisticated machines to deposit this material. You can just directly coat it very easily. There are several methods, doctor blading, just get deposit the material with a plate. You can just deposit this material. Okay, and another is like painting or screen painting, and another thing is spin coating. Okay, there are these kind of the methods you can use to make these solar cells, which are solution processable. And another thing is there is you can search about the roll to roll process. Okay, or spray coating. Spray coating is like spraying the material over a substrate, just spraying. Okay, so these are the methods from which you can make these kind of solar, which are very easy and which are very cost effective. That's why these solar cells are the kind of the research focus of the many researchers. Okay, now, okay, crystalline and thin films solar cells. Why? What is the difference, kind of? So in terms of efficiency, a crystalline solar cells is high, and thin film solar cells are gaining the momentum, and but they will compete. Okay, definitely they will compete, but we need more. If we can stack up several layers of the absorbing material, we can increase the efficiency also. Module cost, it is very high, and it is very low. There is almost very less cost to make a solar cell. Okay, and reliability, it is very good, and they are not that much reliable because they are not that much stable in the outer environment, but research is going on, and definitely we will achieve that aim. And ease of manufacturing, it is low, and very easily these can be manufactured, very highly high ease of manufacturing is there. These are earth abundance, that depends actually in crystalline solar cells which are made from the soil only, silicon. And this depends which material we are using. There are several materials that we can use. future prospect, both have the future prospect. Crystalline, which are a bit highly efficient, and for long run these are good, and these are very less expensive. So these will also cover the market, and very less expensive for the IoT purposes and for all these things. So less efficient, but uh, for the applications where are we going to use them, we can use for the different applications in your remote, in your calculators. So these kind of thin film solar cells are being used in these cases for IoT purposes and all, where low power applications are used. Okay. So, yeah. so so we can it's more than 8 now, so we can stop here. So if you have any question, you can ask now. So do you have any question?